So we are going to discuss the multiplication of the matrix. That's my next property. We write here multiplication of the matrix. Of matrix, we have two matrices we take, A and B. I want to multiply. We have matrix A, we have matrix B. I want to multiply this, and we get here matrix C. So very interesting is here the size of the matrices. So for example, I have here matrix A. Matrix A is having n rows, and we must have here, for example, matrix A is having r columns. So if the matrix B must have here r rows, and it can be having m columns. So when we multiply them, the result will be n rows and m columns. So this is very important, that here the values we are having in between, that is for our rows and columns here, they must be equal. Then we can multiply. If they are not equal, we can't multiply. They are not of the same size. As in addition, we say it's the same size, but here we have the condition. I take an example for this one, that can we multiply these two matrices. For example, I have matrix A. My matrix A is 2, 1, minus 1, 2, 3. This is matrix A. This is 2 by 2. I have matrix B. My matrix B is having 3, 5. Can we multiply it? Yes, we can multiply it. But if I just here take 7, can I multiply? No, I can't multiply. Sorry, this is here is 2 by 2. This here is 2 by 2. So it's 2 rows. Here is these two columns, and there are 3 rows. The columns must be equal to the rows. Here the columns are 2, and here the rows are 3. So when to want to multiply it, this must be 2. So here we can have two rows, but we can have any number of columns. We can have here minus 1, 3. I get here 4, 6. We have 9, 11. So this is, the size is 2 by 4. This 2 rows, 4 columns. So here is 2 by 2. Multiply by 2 by 4. This my A, this my B. Then my C will be equal to, this will be equal to 2 by 4. This is my C, and we can multiply it. But as you know, if the columns are changed, then we are not able to multiply them. They are equal. This one thing, that we must have the rows here must be equal to the columns. So this thing we must always remember. The number of rows, number of columns of matrix A is equal to number of rows of matrix B, and the result is m by n. I take an example for this purpose to show you how we multiply it. Example for this, for the multiplication, I take matrix A. My matrix A is, let's justify my matrix A is 2, 1, 3, 4, 1, 5. This is my matrix A. I take matrix B. Now you can see here, this is my 2 rows and 3 columns. So matrix B will be having 3 rows. This here is 1, 2, and 5. And second is minus 1, 1, and 3. So I can see here, this is my 3 rows and 2 columns. I can multiply it. So the idea for multiplication is, we can have here AB. I can write this result as first row, first column, I get C11. I get here the matrix, this C, this AB, that's equal to 2 by 2. C12, C21, C22. For example, I'm just writing here C22. So this is the result. What's my C11? My C11 is first row multiplied by the first column. This 2 multiplied by 1 plus 1 multiplied by 2 plus 1 multiplied by 5. So my result will be equal to here 2 plus 2 plus 5 equal to 9. I have taken this row and multiplied with this column. This is my C11. First row, first column. C12 in my first row and second column. So it's 2 multiplied by minus 1 plus 1 multiplied by 1 plus 1 multiplied by 3. So get minus 2 plus 1 plus 5 plus 3. So second column we get here 3. So I get here 3. So get here 2 minus 2 plus 4 is plus 2. Now I take C21. C21 means the first number shows the row of the first matrix, and second number shows the column of the second matrix, matrix B. So I take the first row, multiply the first column. I take the second row, multiply the first column. I get here 3 multiplied by 1 plus 4 multiplied by 2 plus 5 multiplied by 5. So I multiply it and simplify this one. I get here 3 plus 8 plus 25. So this will give me here 36. 11 plus 25 is 36. Now C22. C22 means second row and second column. Second row is 3, 4, 5. Second column is minus 1, 1 and 3. So get here 3 multiplied by minus 1 plus 4 multiplied by 1 plus 5 multiplied by 3. This row is 3 multiplied by minus 1, 4 multiplied by 1 and 5 multiplied by 3, and then we add it. When we add it, we get here the result equal to, this is my result, get here minus 3 plus 4 plus 15, that's equal to 16. So I can write my matrix A cross B. This may AB is equal to A multiplied by B. This is equal to, we get here 9, then we get here 2, then C21 is 36, and C22 is 16. So that's my solution of the matrix. I multiply here the two matrices A and B, and we get the matrix here. The size of the matrix is 2 by 2. A very interesting result if we just take as a note, and we are going to apply this one. I take as a note, and I want to write BA for the given example. What is the size of the matrix B? So if I want to multiply here BA, size of the matrix B is, here is my B, 3 by 2. 3 by 2. And what is the size of the matrix A? Is 2 by 3. So what is the size of the matrix C? That's 3 by 3. So here what we get? This is my C, this A cross B, this is 2 by 2. What I'm getting here, 3 by 3. So always I say my AB is not equal to BA. Sometimes we can't multiply it, and sometimes you multiply, the result is not the same. Sometimes the size is same, but the value will not the same when you multiply B by A. So this is my note that we can have here. A cross is also a property that A cross B. But here when we add it, we say A plus B is equal to B plus A. When we multiply it, they are not. Even this is not possible to multiply. It's possible to multiply because here the number of rows and number of columns and number of rows are same, but the result is not same. Even the size is not the same. Two matrices are equal when their size is equal. Here they are not equal. But even as I said, that we having the values equal, but they will be not equal. I give an example for you. I give you another example. I am having here matrix A. My matrix A is 2, 1, 3, 5. I have matrix B. My matrix B is 1, 5. This here is 2 by 2, is 2 by 1. We can multiply them. So my AB is equal to, first row multiplied by first column is 2 plus 5. Second row multiplied by first column is 3 plus 25. So my result will be equal to 7 and 28. Is okay. So this here is 2 by 1. This is fine. We can multiply it. Now if we write here BA, BA means we are having 1, 5, and we are having the other matrix is 2, 1, 3, 5. So we are say it's not possible. Here is this is 2 by 1, and this is 2 by 2. It's not possible. We can't multiply them. It's not possible to multiply it. So here, as I said, we can say AB is not equal to BA. Even we can't multiply it here. Here we can't multiply it. So as I said, we can multiply it, even then they are not equal. So I give another example for the matrix multiplication because that's very important. That's why I want to make it more clear. I have matrix A. My matrix A is 2, 1, 3, 0, 0, and 4. I have matrix B. So my matrix B must have 2 rows because here is 3 by 2. This must be 2 by something. So we are having a 3, 5, 7, 1, 2, 0. So this is my 2 by 3. So I can just multiply them. So when I multiply them, I get here AB. So I write my A. My A is 2, 1, 3, 0, 0, 4. And my B is 3, 5, 7, 1, 2, 0. We multiply them. My first row, multiply first column. This here is 2 multiplied with 3 is 6. 1 multiplied 1 is 1. Then first row, second column, we get 2 multiplied 5, 10. Plus 1 multiplied by 2 is 2. Then first row with third column, we get here 14 plus 0. Then I take second row, multiply with the first column, is 9 plus 0. Second row, multiply second column, 15 plus 0. Second row, multiply third column, we get here 21 plus 0. Then we have in the last row, first column, we have 0 plus 4. Then first row, this last row with third column, second column, we get here 0 plus 8. Last row with third column, we get here 0 plus 0. We get here a matrix that is equal to 7. We get here 12. We get here 14. And here we get here 9. We get here 9. We get here 15. And we get here 21. So the last one is 4, 8, and 0. 4, 8, and 0. You can see here, we get the matrix 3 by 3. So these are the ideas that we can multiply the two matrices A and B. We're moving to the next idea, that is the inverse of a matrix. We're going to discuss inverse of matrix. Inverse of a matrix. We start from 2 by 2 and then we extend it to any size. I take a matrix A. So my matrix A is having the elements A, B, C, and D. I just write the formula for finding inverse of A. My inverse of A is equal to I multiply this A and D, and then I multiply B and C, and we are having here, we interchange these two. This become D and this become A. I multiply here by minus, get minus B and minus C. And I say this is my inverse. Here we say this AD minus CB is not equal to 0, because when it's 0 we can't divide by this, so this must not be equal to 0. So we are having here a property of the inverse that when we multiply A with A inverse, we get here identity matrix. So as we say, the way we are multiplying is important, right and left, but here this is equal to same. For the inverse, we multiply from the left or we multiply from the right, we must get the identity matrix, because inverse has the property, when the inverse, for example 5, where inverse of 5 is 1 upon 5, multiply, we get here 1. Similarly, we have matrix A, and we take the inverse of the matrix, we multiply it, we get here equal to the identity matrix, not 1. Not the identity, it's not 1 upon A, very careful. It's a matrix. So we can just have an example, and I show you with the help of example, where A, 3, 2, 4, 5. This is my matrix A. I want to find the inverse. Find A inverse. So I find here AD minus BC. My AD minus CB is equal to 15 minus 8 is equal to 7 is not equal to 0. That means we can find the inverse. Then I can say my A inverse is equal to 1 over 7. Then I interchange these two. I get here 5. I get here 3. Multiply minus. I get minus 2. I get here minus 4. So this is my inverse of matrix A. So I want to check here the property as I was discussing. When we multiply this A by A inverse, we must get the value of this matrix is equal to identity matrix. We look for this property, and we can just show you that this property holds when we're going to multiply it. I just want to write the property. My K is a scalar. My A is a matrix and by B a matrix. I can say I can write K anywhere I like. I can write KA, then multiply by B, or I can write here A multiply with KB. So we can rewrite A anywhere we like. So I just use this property, and also I want to prove that A inverse A is equal to I. So my A inverse is 1 upon 7, and I am having its A inverse is 5 minus 2, 5 minus 2, and then we having here minus 4 and 3. And we multiply here, this is my A inverse. I'm writing here this as is into A. My A is 3, 2, 4, 5. 3, 2, 4, 5. So I'm writing here this is my A inverse. So I multiply them. I get here 1 upon 7 out. First row with the first column. First row with the first column. We get 15 minus 8. First row with the second column, 10 minus 10. Second row with the first column, minus 12 plus 12. Second row with the second column, we get here 8 plus 15. So when we solve this one, you can see what we're going to get here, 1 upon 7. And we get here 7, we get here 0, we get here 0, we get here 7. We multiply 1 by 7, each entry, we get here 1, 0, 0, 1. And that's our I. So this is one part. Second part is that we just take here our A and we multiply by this by A inverse. We have multiplied inverse by A. Now we take here A and multiply by A inverse. So my A is equal to 3, 2, 4, 5. And my A inverse is 1 upon 7. I get here 5, 3, minus 2, and minus 4. So as we say, K is just 1 by scalar we can write anywhere we like. We write it outside, we get 1 upon 7. I'm having here 3, 2, 4, 5, multiply by 5 minus 2, minus 4 and 3. So we get here 1 upon 7 is out. And we get here 15 minus 8. Then we get here minus 6 plus 6. Then we're having 20 minus 20. Multiply, you get minus 8 plus 15. We simplify this one. We get here 1 upon 7. Get here 7, 0, 0, 7. Multiply 1 by 7, scalar. Multiply each entry with this one. We get 7 upon 7 is equal to 1. And then we get here 0, 0, and 1. And that's my I. So I can write my property, which I mentioned that this is the property we are going to discuss. That's A inverse A is equal to A inverse is equal to I. So this is the property of the inverse of the matrix.